So what we have here is the world's first biological computer. And why is it biological, you may ask? Well, the reason for that is we grow neurons derived from human stem cells, turn the blood into stem cells, and then we can derive the stem cells and turn them into neurons. So once we got these neurons, what do we do with them? We put them on a computing chip like this. Okay? Now, what do they look like when they're on a computer chip? This is what they look like. So the gray are neurons, and then behind that are the electrodes on the chip. That's 20 microns.
Okay.
The human hair is 50 microns in width. That's like, imagine the hair. That's the axon from the neuron, and there's dendrites and synapses everywhere.
Wow.
So this is the level of complexity of these neural networks. So once you have them on this system here, because neurons communicate with electricity between one another, we can read the activity and we can simulate them. So what we have here is a live stream of neural activity from a laboratory all the way in Melbourne, Australia.
Okay.
So it's streaming over there in DVD to provide a stimulus back. So you now have read-write access to this biological layer. What do you do with it? So we took that and we put it into the video game parts.
Efectivamente, lo que nos están diciendo es que han podido hacer crecer tejido celular, neuronas, en un chip. Y que ahora con este soporte biológico, con esta red neuronal, pues a través de estos estímulos la han entrenado para mover la pala del juego del Pong, tal y como se puede ver en la esquina superior de la pantalla. Y esto me pareció súper interesante. En Deep Learning a las neuronas artificiales las recompensamos o castigamos subiendo y bajando números de una función de coste. Y ya está, matemáticas al poder. Pero, ¿cómo recompensas o castigas a una neurona biológica? Pues por lo que nos han contado, las neuronas han evolucionado para reconocer patrones. Y cuando se les presenta una señal repetitiva cuyo patrón es identificable, eso, entre comillas, es aceptado como una recompensa. Si las neuronas juegan bien, una señal de onda sinusoidal repetitiva será música para sus oídos. Pero si están jugando y de repente cometen un error, si la pelota golpea la pared del fondo, entonces el castigo que se le aplicará será una señal de ruido aleatorio, donde no haya patrón que detectar.
So a reward is like a predictable stimulus, a predictable information. So like a sine wave. You hit the back wall, we give you white noise. So very random, unpredictable information. Yep. So this is a paper, or actually a poster that we put out at NeurIPS. And what we showed was we said, we're going to give the reinforcement learning agents the same amount of information that the neural systems got. We're going to benchmark it. The mouse cortical cells and the human cortical cells outperform reinforcement learning agents.
Nice.
So this gave us a really interesting insight. We said, wait a minute. So these cells are using 10 to the minus 4 watts of energy, and they're using far less data. Because that's what we're good for, right? We use 20 watts of energy and we're operating in real time. Could these systems be the future of intelligence? Right? Now that we've proven all these things, we need to start thinking about how do we keep these cells alive outside of the human body. So we developed this product. It's called the CL1. So this is an artificial life support system. The neurons would be in here, so you can think of this as the brain. These are pumps that circulate the cell culture media. This is the feeding reservoir. This is the waste reservoir. These are filtration units, like the kidneys. This is a gas exchange system, like the lungs. So having all of these systems in place and a heating element underneath, and you can see the parameters in the front, keeps the cells alive for extended periods of time. And then what we do here is we have this device. It's our, neural link that we can then plug in and make contact. And that connects with a compute unit at the back that then does all the processing of the information. One of the last thing that's quite interesting is that what we learned was that if you take blood cells from patients with epilepsy and you turn them into neurons and you put them into the system, the neurons in this system will also have epilepsy.
Wow.
Yeah. And they're also responsive to medications.
Okay.
So this opens up a new avenue for, can we use this for new novel drug development or personalized medicine? Or you take baseline normal cells and you can CRISPR them with mutations. And then you can see what the delta is.